Thank you so much, Risa, and thank you, everyone. I'm delighted to get us started with the first session of this conference, Mapping the Sky. So Mapping the Skies, in the space of about 3 hours, our speakers will take us from right here on Earth to the Milky Way, distant galaxies and beyond, all the way to the edge of the observable universe. So please fasten your seatbelts. The first speaker, we're very thankful to have Gregory Green, who is the Sofia Kovalevskaya group leader at the Max Planck for astronomy. So thank you for coming all the way. Greg joined KIPAC from 2016 to 2019 as a Porat Fellow after graduating from Harvard Astronomy. He's an expert on all things galactic structure and dynamics, and in particular on the three-dimensional inference of the dust and star distributions inside the Milky Way. So prepare to be wowed, and please welcome Greg for us.
Does everyone hear me fine? Okay, great. Hi, so I'm Gregory Green, and I was here from 2016 through 2019. I want to give you a little bit of an introduction to what BPRP spectra are. So these, we sometimes call them XP spectra because we get tired of saying BPRP all the time. And this is basically extremely low resolution spectra. So we can even call it maybe many band photometry. And it's being done with Gaia. And so Gaia has two optical paths that come in. And these two optical paths get put onto the same CCD. And then there are two bands of CCDs here and here, which are dispersed at very low dispersion. And those give us some very low resolution spectra for basically every star that Gaia observes. So these are something like R of 50 to 160. And they're slitless spectra. So in dense regions, they overlap. And they're optical. And currently, there are 220 million stars that have these spectra. So this is kind of what these spectra look like. You can see that you can see features in them, but this is a far cry from high resolution spectroscopy. And so I'm going to compare this with LAMOST, which is a large ground-based spectroscopic survey. So compared to LAMOST, Gaia has 20 times as many stars, but about 1/20th the spectral resolution. And one important thing is that Gaia XP spectra are flux calibrated. So we actually know what is the true flux, not just the continuum normalized flux, but we actually know the true flux of every star. And it's also all sky and has a very uniform selection function. And those are two really important things if you're going to be mapping the sky. So what we want to do, the first thing we want to do, if we want to map dust, we typically have to actually know the types of the stars. So for example, you need to know the temperature of a star in order to disentangle the temperature from its extinction. And so what we want to do is we want to use these low resolution spectra to determine the type of a star. So that for me means T effective, F over H, and log G. And one obvious way to do this would be something like some machine learning approach. So that would be where you go from the spectra and you have some training set that has labels, and you directly learn how to put these spectra into some black box and get out the stellar type. So this is a very common approach that's taken. Another approach is to cross-match with something like LAMOST, which has high resolution spectroscopy. And from LAMOST, you can actually do a proper, very principled model to get T effective, F over H, and log G. And so for the small set of stars that have a cross-match with LAMOST, you can get those parameters. And then you learn a forward model that says, okay, I have some stars that I have observed the spectra from. I have their parameters, and I try to learn a model that tells me how to go from those parameters to BPRP. And then once you have a forward model like that, you can actually do something more rigorous, like Bayesian proper MCMC or something like that to determine the parameters. So the way that we're going to do this is, so we have cross-match, a cross-match with LAMOST. We learn this model that tells us how to map from type to the flux. And then we use this to infer the stellar types, extinctions, and distances of all the stars that are observed by BPRP. And we also include some near-infrared photometry just to help us get the extinctions more accurately. So this is our cross-match. This is a Kiel diagram of our crossmatch with LaMost. So about 1% of the stars observed by BPR and BPRP have LaMost spectra. And we bootstrap this 1% of stars to learn our model and then determine the types for the other 99% of the stars. So our forward model basically has some type parameters, parallax, and extinction. And then it also has some overall model parameters, which are basically saying how do you map from stellar type to flux. So those are a bunch of neural network weights and an extinction curve. So this is kind of what our model looks like in a diagram. You take the atmospheric parameters and you put them through a neural network that gives you the flux at 1 kiloparsec. And then you take into account the parallax and the extinction, and you predict what the flux should look like. So it's a combination of a principled model that has, takes into account the correct effect of parallax and extinction, but also a model that goes from, that's sort of more of a black box, that goes from atmospheric parameters to flux at 1 kiloparsec. And what we actually do is we actually minimize the chi-squared of this entire model. So this is showing a comparison of our model versus an observation. And we're trying to minimize this chi-squared for every star and also for the entire model. So we're actually learning all the neural network parameters, everything, to try to minimize chi-squared across the entire data set. And so how we do that is we begin with our set of stars that have LaMost. We assume that LaMost is correct, and we hold the stellar parameters fixed, and we just update the model. And so we just update all the model parameters until the chi-squared is minimum. And then we say, OK, now we have our model. And then we go and we refine the stellar parameters. And so we say LaMost is a prior, but it's not necessarily exactly correct. And then we go back and forth, and we convert, and we keep on updating the model, updating the stellar parameters until we have an optimal model that has both stellar and model parameters. And all this is implemented in an auto-differentiable framework, TensorFlow. So actually, when I was at Stanford, a lot of before I came to Stanford, I didn't do any sort of machine learning type stuff. But actually, I feel like after coming to Stanford and being exposed to all the machine learning here, I've basically started using TensorFlow much more heavily in my research. So this, even though it does have a proper Bayesian formulation, actually tools like TensorFlow are incredibly powerful for implementing these models. OK, so this is what our models look like. So this is a model here of wavelength versus flux for stars at different temperatures, learned entirely from the data. And you can actually see that we're picking up lots of features. For example, metal lines that change with temperature. You can see the Balmer lines as well. So there are a lot of correct features that you would get out of a proper stellar model. But this is all learned entirely from the data. OK, and we also learned an extinction curve. So this white line here is showing extinction versus wavelength. And this is for, we only here have a universal extinction curve, so no variation in the dust properties. And then here in the background, I'm showing a literature extinction curve that was determined, actually 40 years ago now. And we're kind of smack dab in the middle of what average Milky Way dust should look like. OK, so we did this first, this initial work, and we published reddenings for about 100 million stars. Well, there are 100 million stars that have really clean distances in reddenings. So I'll show you what this looks like. Oh yeah, all the data is available online. You can download all of our extinctions. You can actually query them really simply using code like this. And the result along individual sightlines looks sort of like this. So we're looking here towards Orion. And distance and extinction, so distance is on the x-axis, extinction's on the y-axis. And you can see very close by towards Orion, there's no dust. And then you reach the distance of Orion, and all of a sudden there's a lot of dust. And then these are all the background stars. It used to be really difficult to turn these sorts of measurements into a three-dimensional dust map, because it used to be that the uncertainties in these stars are really large, or much larger. It might be hard to tell here, but there actually are uncertainties on each of these stars. They're just incredibly small. And now it's kind of trivial to figure out what is the distance to a dust cloud, because we have no dust, and there's a pretty sharp transition to having dust. So if you look at a couple different sight lines, these are just various famous clouds. You can see where the dust clouds are. So for example, Taurus now you can tell is between 100 and 200 parsecs. Perseus, Madalena. So anyways, because these dust maps because these extinctions and distances are so accurate now, it's really easy to make 3D extinction maps using this. So I'm going to show you some really preliminary results, which are purely based on taking stars at different distances and just averaging the extinction. So it used to be that we had to do a very complicated Bayesian inference to determine what the extinction in 3D was, but now it's actually quite simple. This is just purely taking stars at different distances, averaging their extinction. And so now I'm stepping out in distance, and you can see how the extinction builds up. And you can do this in a differential way. So this is now taking the difference in average extinction at different distances. And so this is the nearby clouds, and then farther and farther away clouds. You can see this goes negative as well because I'm just taking the straight average. And it could be negative, but it almost never is negative. So you see almost only red here. And then we can look at individual clouds. So these are just various regions of the sky showing the average extinction out to certain distances. So this is galactic center out to 500 parsecs. This is Ophiuchus, Aquila South, and the galactic Dendros anticenter out to 2 kiloparsecs. And then this is zooming in on Orion, Lambda Orionis, and then California, Perseus, and Taurus. So you can see that we're tracing a huge amount of very detailed structure at many different distances purely using these Gaia XP spectra. And then we can also take a bird's eye view. And so this is looking down in the galaxy. The sun would be here. And going in the galactic center would be out in this direction. So probably around here, actually, off our map. And you can see this is the local structure. So you can see various linear structures in the Milky Way locally in dust. OK, so far I've assumed that the extinction curve is universal. There's only one type of dust. Dust never varies in its grain size distribution or chemical properties or anything. So if you look in any direction, you only see the same extinction curve. Obviously, that's not true. Typically, we know that as you change the properties of the dust, that you get different amounts of extinction at short versus long wavelengths. This is normally parameterized by something called RV, not to be confused with radial velocity. This is the dust RV. It's just basically a ratio of optical extinction to optical reddening. So this is a famous set of dust curves from Fitzpatrick et al., actually just Fitzpatrick 1999. And you can see that in the optical, it just sort of changes the slope of the extinction, changing RV. So if you actually look at our model and say, OK, what do we predict the flux should be for all of our stars, given our model? And you look at the average residuals in different wavelengths, you see that everything's sort of fine at the shortest wavelengths. But then at the longest wavelengths, actually we have sort of large residuals. And these residuals are not just all positive or negative, and they actually kind of look like the dust. So this blue here, it looks a lot like various dust clouds. This red here is Ophiuchus. So if you have residuals that are positive or negative that are correlated with the dust, that kind of implies that something's wrong in your dust model. And what we actually think is going on here is that there's unmodeled extinction curve variation. So in our original model, we had just one extinction vector, which is universal for all the stars. We modify that by introducing a dust property variation, which basically says that every star can be through a different type of dust. So we do the whole thing again where we train our model. We go from having this extinction curve that's universal to having an extinction curve that is that has some variation that's parameterized by this Xi variable. It's sort of the Xi variable is basically like RV. So we train our new model, and this is what we get out. So this is our extinction curve model now that's completely learned from the data. It looks very similar to literature extinction models. So this is, for example, taking the percentage difference between our model and a very new model by Carl Gordon that was just published this year. And you can see that on average, we agreed with Carl Gordon to within a couple %, purely learned from XP spectra. And then we can compare to different reference models and get similar results. Actually, interestingly enough, we agree more with the more recent models than we do with the earlier models, which I guess should be expected. So now we can infer this Xi variable, which is basically like RV for every star. And we get out a map of what RV variation looks like across the sky. And so you can see different dust clouds have different RVs. And I think this is actually, so far, this is, I think by a very large margin, the largest number of stars that have measured RVs that have been published. So this is something like 100 million stars with RVs. And we can zoom in then on different clouds individually and look at, on a very fine scale on each cloud, how do the dust properties vary? So this is zooming in on Orion A, and you can see that actually in the Orion Nebula, which is right around here, there are very high RVs, and this is on a very local scale. The same thing in Taurus. In some of the dense regions, we have very high RVs. This isn't the case everywhere, so different clouds appear to have different variations in chemistry. So in Pipe, for example, we don't see a clear correlation between the density of the cloud and RV. And Perseus is also sort of complicated picture. And then Ophiuchus is something that's totally different from everything else as far as we've seen so far. Ophiuchus is a region that has very high RV, even in the very diffuse regions. So I think that this is something that really is worth exploring, or this is something that we really want to now investigate. Using our measurements, why do we see these different patterns of RV variation in different parts of the interstellar medium? So I think there's lots of work to do. I'm going to throw out a few ideas. One is that this could be dependent on the interstellar radiation field. So what is the radiation field doing in each of these clouds? We want to also correlate this with molecular gas and see how RV is correlated with these dense cold regions of the interstellar medium, and also correlate it with star-forming regions. And there are probably many other things that we could try to correlate about the properties of the interstellar medium. So just in summary, we've published now 100 million exquisite stellar distances and extinctions inferred from Gaia XP spectra. We've also determined extinction curve variation, both on large and small scales, and we've determined RVs for really an unprecedented number of stars. And I think this is really just the beginning, because now that we have this huge data set of how are the properties of dust varying in the interstellar medium, we can try to correlate that and understand physically how this correlates with different properties of the ISM. So that's what I wanted to present. Thank you.
Great. Thank you very much, Gregory. We have time for questions. So please wait for the mic so that everyone can hear us online, and otherwise we'll repeat the question. Vahe?
Question about that last part.
Yes.
What does RV mean? How is it related? It must be complicated relationship to size, shape, and composition of dust grains.
Yeah,
How easy will be that task of determining all those properties of dust?
So I think that to first order, RV should trace something about the grain size distribution. Because if you think of it, the simplest model is larger dust grains can more efficiently block large, or can more efficiently scatter and absorb longer wavelength light. So if you have a higher fraction of large dust grains, then you have a flatter extinction curve. And if you have more small grains, then you have a steeper extinction curve with wavelength. So I think that's the first order. That's the first order property that you're measuring. But then the interesting thing is what actually determines the dust grain size distribution. So then that has to do with how grains are coagulating and also how they're being destroyed by various properties like the interstellar radiation field.
You don't have any polarization observation?
No, we don't have polarization.
Yep, at the back.
Hi. So you showed these nice red-blue color maps of kind of the global variation, and then you zoomed in on individual clouds. And I think this information was on the plots. I just didn't read the color bar in time, but I can see now. I was going to ask if in the variation inside a single cloud, if it was the same kind of scale of variations that we're seeing on the global map. And it looks, looking at this bar now, it looks like that's the case.
Yeah, so we see both large scale and small scale variations. So for example, here, if you look at, let's say, Orion, you see this, Orion here just looks like it's sort of low RV. But then it turns out that if you really zoom in, you see, okay, low RV around Orion, but then right inside some of the densest regions, you have very high RV then.
Mhm.
So they're, yeah.
Yeah, and the blue here would also show up as blue on the previous map, right? It's the same,
Yes,
the color scale.
they're not exactly the same. The color scales change a little bit because they have sort of a different average in different clouds, but it's similar scales. Yeah.
Okay, thanks.
Any other question for Gregory?
Great talk. I just want to say I use your maps pretty much every day. So yeah, please keep making these. I had a quick question. The plot where you showed the extinction near Orion, where you can kind of see it jump up,
Sure.
and you pointed out the error bars are very small. The error bars are much smaller than kind of the scatter. Is that just the like fine scale structure in the cloud, and that basically different lines of sight, you see different extinctions?
Yeah, this is I can't remember if it was like 1/4 of a degree, something like that. So on that scale, you do have a lot of variation. So this scatter here is, I think, real scatter in the cloud.
Okay.
It's not just that the errors are underestimated. I think it really actually is real scatter.
Great. Any remaining questions for Gregory? Yep.
Yeah, I was just wondering, out of curiosity, the neural network that you used, what type of architecture did you choose to adopt, and like, how did you like make that decision in making this model?
Yeah, so this is sort of like a schematic picture of our model. The neural network itself is very simple. It's just a feed-forward neural network. And we did that because we feel like this is just being used essentially as an interpolator that says we have a bunch of atmospheric parameters and we know what the flux associated with those is. And so we just want a function that basically smoothly interpolates between the different measurements that we have from LaMost. So this is fairly simple. However, the rest of the model is physically informed. And so we put in, parallax, we put in the 1/r² law, for example, for parallax. And then we put in that we know that there should be something like dust. We said we don't know what the extinction curve is, but we know that there is an extinction curve. And so this is a combination of some sort of just interpolator with an actually physically informed model for the parts that we do understand better.
Okay, thank you.
And we have time for one more question.
How do you expect this to change with new Gaia data and also with, data like we'll get from LSST?
Yeah, so with new Gaia data, the first thing is currently we have 200 million stars that we've been using. The next Gaia release, I think, is going to have something like 800 million stars with XP spectra. So it's just going to make, far more stars that we can use to trace on even finer distance and angular resolutions, both the dust density and RV. And also the quality of the data should be improving as well. LSST is going to give us, it's going to go much deeper than this goes. So this is out to, it really depends. Like if you're going towards a galactic center, this won't reach nearly as far as LSST will. So LSST is going to allow us to trace really like in the galactic plane to much greater distances what the dust is doing. Yeah.
Great. Let's thank Gregory again